all for coming. Flattered to see that everybody didn't just immediately avoid my second talk after the first. So I must. Well, there we go. Now you don't know what you're in for. So I will briefly review what we talked about last time. What we spent last time doing is constructing the exterior calculus part of my talk. I just showed that one could, in fact, construct an object with all the properties that I'm about to write down. Today, I'm just going to write down those properties again for the benefit of those of us who weren't here last time or who have filled their head with more important things in the intervening time. So first off, last time I introduced de Rham cohomology and the Cartan-de Rham complex in the context of a slightly different object than smooth manifolds, where people are used to seeing these things, something called C-infinity algebras, which is sort of actually the natural home of these functors, these cohomology functors. So I'm going to redefine that for all of us briefly. So a C-infinity algebra is a pair where A is a non-empty set and phi is a parameterized collection of operations on A, parameterized by all of the C-infinity functions from finite dimensional Euclidean spaces to R. So with less words and more symbols, for all f in the infinitely differentiable functions, in the usual real sense, we have that capital phi of f is going to be an operation on A with the same arity as our function f. So this parameterized collection of operations has the following additional properties that it has. It sends coordinate projections to coordinate projections. So if I have acted this operation on some n tuple of elements in my algebra, and the parameterized function was the jth coordinate projection of my underlying Rn, then we just get the jth coordinate projection on A to the n. Similarly, if if I have a function on n variables constructed in the following way. So he is a composition of a function on m variables with the product of m functions on n variables. So if, this is something that we can do with smooth functions. We can take products. Those are smooth functions. We can recompose with another smooth function. Smoothness is preserved under composition. So this is another totally genuine smooth function. And what we would like to be true is that the operation associated to this thing ends up breaking up, decomposing in exactly the same way that our parameter functions have here. Oh, no, not G. Capital phi. So there we go. Contain, for those of us who weren't here last time. M and N not necessarily the same. M, N, just non-negative integers.
Well, shouldn't M then be at least less than N?
No, we could have n variables, and then you could just have one function that you're composing with another function, or vice versa, one variable, and you're composing m of them.
F is defined on?
F is defined on here. Let me actually. F belongs to, in different F now, belongs to R, M, R, and each of these G's, G sub j, is in C infinity Rn, R. So each one of my original G's was just a function on Rn. When I took them and producted all m of them together, that gave me a smooth function from Rn into Rm. F was always a function on Rm, so I could compose them. And that's where I wound up with that guy. Okay? And contained in this is an infinite collection of identities on all of my operations. Contained in him is the usual associativity of multiplication and addition, as well as commutativity and the fact that one works like a multiplicative identity. All of that is contained in there. So the typical example of such an object. Sorry. Yes, every C infinity algebra is a commutative algebra, and in fact, it's actually an R algebra. R will be, as long as it's not just the zero algebra, R will be embedded in this algebra. It'll have a subfield R in it. And the typical example of this guy is just the collection of all smooth functions, smooth real-valued functions on any smooth manifold M. This will have the property that if you take such a set, if you take n of his elements, product them together, you'll get a function from M into Rn. You can now compose that with a function of n variables, which is also smooth. You'll get another smooth function. So that's where the, and that is exactly the C infinity operation structure on one of these canonical smooth algebras. It literally is just products in composition in exactly the same way that I've written here. But abstractly, it doesn't have to be that. Okay, so, and since it was brought up that these are algebras that have some properties, the fact that I have used real operations to define them does give them properties that have to do with real algebras. In particular, all of these algebras are something called formally real. So if I have n elements of such an algebra, and I add the sum of their squares to 1, this element is multiplicatively invertible in my algebra A. For the reason being that the function not equal to 1. This is invertible, multiplicatively invertible. His inverse exists. And the reason is because the function 1 over the sum of the squares is a smooth function. So he's got to be one of the operations. I've got to be able to put n of my elements of my algebra through him. But obviously, now if I have this element and I multiply it by this thing unreciprocated, I'll have to get 1 following from these identities here. So in particular, this means that the complex numbers, the plane of complex numbers, can't be given a C infinity algebra structure, because otherwise this would very clearly contradict the fact that I squared is minus 1. All right. So last time, we defined the first thing in the title of my talk, the exterior calculus, again, which is normally built on C infinity functions on smooth manifolds, but which lives much more naturally in this algebraic setting. So I won't repeat the construction, but I will repeat what we ended up with. So we ended up with a new algebra omega, which had a couple properties. It's an A module. So it is a module that admits an A multiplication. It's filtered by the different forms of various order. So to make that more concrete, where now omega j is the j forms, the order j forms on A, which for those of us who don't think about differential forms very often, they look like this. It consists of else look like sums dj is equal to 1 up to n of now a sub j 1 0 even d a sub j1 wedge, where this wedge product that's shown up is familiar to some of us, but for the rest of us, I'll go ahead and write down his properties in a moment as well. Oh, I'm not allowed to use j as my index. Apologies. I love using j as an index. I love it so much that I will overuse it constantly. Okay, so every single one of my k forms looks like a linear combination of these fellows. These resemble good old-fashioned differentials for those of us who have seen differential geometry before, but as we saw last time, they can be arrived at much more quickly, though perhaps with much less intuitive meaning to what they actually are, just by using a very universal quotienting procedure. All right. So it comes with a graded commutative product. Wedge, so called the wedge product. Which we've already seen here, but has the graded commutative property, which means that if I were to go ahead and wedge two forms together, then I could swap them at the cost of a sign that depends on the degree of both alpha and beta. When I wrote this down last time, I only wrote the degree of alpha. I was wrong. Thank you all for not calling me on that. So there we go, graded anticommutative. So in particular, if we have one of the forms being of even degree, it's just commutative, because obviously an even number times an odd number is still even. All right, so we've got a module, it's filtered, it's got a graded commutative product, and it's also got a differential, a derivation. And this derivation is related to the usual exterior derivative. But again, we defined him in a different way. It turns out that at the level of the very first filtered element, omega 0, this turns out to be the universal derivation on omega 0, otherwise known as just A again. Universal, that means that it sort of contains all of the information of any derivation on A. Any other derivation can be arrived at by just composing some homomorphism into another module with this D, again, restricted to the filtration at the level 0. So it has two different properties which make it reasonable to call this thing a derivation. It has a chain rule that it satisfies with respect to the scalar multiplication part of such elements. So if I were to just go ahead and write A0, D1 wedge, all this extra junk, AK. So there we go. That's a basic element. Everything in the space of K forms is sums of these guys, and D is additive. So if I just show you what happens for one of these guys, you know what happens for everything. And I should also set myself up to actually use the chain rule. I'm going to go ahead and say that this is B1 up to Bn. Apologies for how scrunched that got. That's an operation function f acting on n elements labeled B1 through Bn. And what makes this thing a derivation sort of in the usual sense is that it satisfies the usual sort of chain rule for this guy, so f. And I've adopted a bit of a shorthand here. When I'm only working with one of these C infinity algebras, there's no real reason to keep bringing up this capital phi of f thing. I'm just going to write the operation using the parameterized function f. This won't cause any confusion. And then what's left over is D applied to the jth fellow, so Bj, and then wedged in with the rest of the elements that were left over. Okay, so that's its first derivation property. It has the usual chain rule in its scalar multiplication argument, but it also has a graded Leibniz property, a graded product rule, with respect to the wedge product. So again, I'm just going to show you how it acts on individual filtered levels, because once you know how it does that, you just use it additively, you figure out how it acts on everything else. So I'll just have good old alpha and beta, just like before, but unlike in the graded commutative property, now this really does only depend on the degree of the first one. So we wind up with d alpha wedge beta plus minus 1 to the degree of alpha times alpha wedge d beta. So So there we go. This is the exterior calculus. There's just one extra property. And this is going to be very relevant to discussing cohomology. This derivation closes on this algebra, meaning that the derivation composed with itself is always equal to 0. Yes, this one only depends on the degree of alpha. Sorry, that degree kind of got smushed. All right, and so this is what we spent our time constructing, and the reason why this matters to the discussion of de Rham cohomology is, in fact, these individual filtrations, together with the restriction of D to those filtration, gives us a cochain complex, the Cartan-de Rham complex, and the cohomology of this complex is the de Rham cohomology. So just briefly, oh, not 0, just nope. I just keep wanting to write down short exact sequences. I can't help it. Okay. So there we go. This is where we left off last time. We're all caught up. Everybody's now an expert on de Rham cohomology and C-infinity algebras. Way to go. So de Rham's theorem is about showing that this cohomology on smooth manifolds is isomorphic to a different choice of cohomology, one that we haven't discussed yet. And so it would be prudent to define that as well. So now I'll go ahead and define singular cohomology for all of you. And don't worry, I don't need to bring up any weird categories to do it. So and this will also give me a great example to discuss the differences between the various forms of cohomology theories. I'm going to bring up something called the Eilenberg-Steenrod axioms in a bit. They're sets of axioms, rules that homology and cohomology theories satisfy that make them easy to calculate. But what form they take depends on whether the underlying category is like a category of algebraic or spatial objects. And it also depends on whether or not you are looking for a homology functor or a cohomology functor. Each one of them causes a couple of changes, and you have two different changes that you can mix together. So there's sort of like a quadrality of different cohomology axioms, Eilenberg-Steenrod cohomology axioms we can write down. And we'll see how these two differ once I finish writing this one. Okay. So the starting point for this theory is the topological spaces. This is the natural home of singular homology and cohomology. So X, a topological space. Sigma n is the standard, n even, is going to be the standard n simplex in Rn plus 1. I'll define it here for a second. But these individual simplices are going to be, they're going to some way be a replacement for the forms that we have here. We're going to be taking a free abelian group over these maps from this space into our topological space. And then that will exactly give us the chain complex where before we had a cochain complex. All right, these are convex hull of the points. E1, even E1 through n plus 1 in Rn. So, and where by these EJs, I just mean the standard basis vectors. So, it would be a degenerate simplex. Yeah, it would degenerate down. Yeah, it's allowed. It's just the purpose of keeping them all separate is so that I ensure that the simplex I wind up with is the right dimension. All right, so from each one of these fellows, we define a singular n simplex on our space to be a continuous function from this standard n simplex that I've written down a second ago to our topological space. So that singular simplex, hence the name singular homology. basically n simplex. And now in order to make my chains, my n chains on this space X, I define this to be equal to the free abelian group on these singular n simplices. Free abelian group on singular n simplices. Yes, this is just a continuous function from my standard simplex into space. Yeah. And he doesn't have any other properties. This is where the notion of singularity comes from, because this could just be a constant function, right? It degenerates my simplex down to a point in the space. That's totally okay. That's not going to ruin anything. So yep, everybody clear on how we construct the free abelian group out of a set? All right. So then now all I need to do in order to make a chain complex is I need to tell you what the boundary morphisms are. So again, this is a co-chain complex. What makes it a co instead of a chain complex is that each of these co-boundary morphisms, in this case, increase the degree of our chain instead of decrease it. So here what I'm looking for is maps that are very similar to the Ds that I've got above. They compose together to 0. But instead of going up in degree, they go down in degree. To do that, I'm going to need to introduce something else related to the singular n simplex. So we're going to let, oh, do I have an eraser? Nope, I'm just going to keep erasing things with my hands. Okay. Oh, thank you. All right. So do k and n. All right. So this map is going to be the inclusion of the kth face into the singular n simplex. So it'll be from the n-1 simplex, which every single face of an n simplex is an n-1 simplex. Here. I'm a category theorist, so I got to use my curly arrows. That's how you know that I know category theory. Okay. So that, by the way, right hook arrow just means inclusion, usually, or embedding. So this is just the embedding of the kth face into my n simplex. So it has k plus 1 faces, and you embed each one of them. And technically, there's a discussion of orientation to be mentioned, but the induced orientation on subspace.
So you have sigma n-1 and
Yes.
sigma n.
Yes.
So
What's k? Oh, thank you. So let me tell you what the image of this guy is, because that's where k comes up. So I, k, n of the standard n-1 simplex is exactly convex pole of I have n plus 1 of them. And we get rid of the kth element. So this operation that I've done here, just taking the convex hull of all of the other vertices except for one, that will just give me one of the faces. And when I remove the kth vertice, then that's giving me the kth face. It's the one that's opposite to the kth vertex. So that's what's actually making these things depend on k. Okay? So there we go. I've got my boundary inclusions, and from these boundary inclusions, I can go ahead and define my boundary map in the following way. So I'm going to define it, again, on individual singular simplices, because, again, the free abelian group is just a sum of these, or an integer sum of these, and you just push this guy right on through the sum and the integer part. You consider him to be additively extended from the original continuous functions. So acting on such a singular simplex, we get that it is equal to the alternating sum this is an n simplex. Okay. Oop. Try not to fall over. All right, so here we go. So we go ahead and restrict our function f to each of these different faces. But we remember which of these faces we're restricting to, and depending on whether or not that is even or odd, we assign a minus sign to the front.
Can I say something?
Absolutely.
Is it kind of a badge of honor not to draw one picture of a pyramid?
No, you're right. It's worth doing. It's worth drawing a picture here. So let me go ahead and draw two simplex even for all of us. Two simplex in 3 space. So here we go. Here's 3 space. We're all very familiar with it, I hope. So the way we go ahead and construct these standards, and off in that direction too. I'm sure you could all imagine. So we go ahead and take the basis vectors. So we have E1 right there, E2 over here, and E3 right here, otherwise known as X, Y, and Z for most of us most of the time. We go ahead and connect these because that's definitely going to be in the convex hull. The way I've drawn this, actually I'm going to move this point out. It might not be technically accurate, but it'll make this drawing a lot easier to understand. And then the singular 2 simplex is now all of these points lying in between our vertices, right? We've connected. This is exactly the convex hull. Because once I have these 2 points over here, I know I have to have the line segment between them. Once I have that line segment, I have to have every single line segment connecting this vertex to every single point on that line segment. That gets me the rest of the points. So that's what all of these different singular n simplices look like. And then when I go ahead and send them through a continuous function into my space, they just, that just like messes them up somehow and sticks them into my topological space without tearing or cutting. Okay? So this alternating sign out in front of my boundary map actually ensures precisely that the composition of 2 subsequent boundary maps is 0. So in the exact same way that we have the closure condition for the exterior differential, we wind up with the closure condition for these boundary maps. And that gives us the singular chain complex n minus 1. Technically, I have to put my space there. Nx. No, it will not be an exact sequence in general. The only time it will be an exact sequence is if all of the different homology groups of your space vanish. So only if you're homologically trivial. All right, so there we go. That's our singular homology, but that's not what I'm showing is isomorphic to de Rham cohomology. Though, historically, that is kind of what happened. When de Rham cohomology was first discovered and de Rham's theorem was first proven, the notion of cohomology hadn't yet been invented. All we had were things like simplicial and singular homology, as Poincaré named them. And so the original de Rham's theorem was proven in the context of something like a Poincaré duality between de Rham cohomology and singular homology. Thanks again, Sam. If it weren't for Sam, my hands would be all nasty by the end of this talk. If only. Okay, so we have singular homology on the board. We can get to singular cohomology very, very quickly because it arises by dualizing the previous chain complex. By which I mean, I define the singular cochains of my topological space. Ooh, and actually, technically, this is where I could have introduced it over there, but I'm going to introduce it over here. we can choose different coefficient groups for our homology theories. And this is going to be relevant to our discussion because the coefficient group for singular cohomology that we need to have the isomorphism with the Rham cohomology is the real numbers. We can't just do it for anything. So I'll go ahead and stick G in abelian group. And this is simply going to be the homomorphisms from our original K chains, just an abelian group, so we can talk about homomorphisms, into G. So at every level we get this. Similarly, we can go ahead and construct co-boundary morphisms. So now they will increase degree instead of decrease it, just like in the Rham case that we have over there. And the way that they're defined is by simply taking the dual of our boundary map. So I'll go ahead and just do this to make it more obvious, because if I just use del for everything, then this is going to be very hard to read. So there we go. Cohomology has upper indices, homology has lower indices, so let me go erase that, do it again. Sorry. Ugh, getting ahead of myself. Really, really want to get over this homology junk. Cohomology is just better, as it turns out, but that we won't be able to talk about why today. Okay, so there we go. Boundary maps, they have the lower index instead of the upper index. And now I can go ahead and define this is just some homomorphism, because that's what these guys act on. And the way that he does that is by just composing first with the boundary operator. So it's very clear that this thing is also going to have the same property as the boundary operator, namely that when I compose two subsequent ones together, I end up getting 0. Because how I implement this map is to compose on the right with the boundary operator, and when I do that twice, that will be 0, and I'll be composing a homomorphism with the 0 operator, it will be 0. Okay, so there we go. We now have our singular cochain complexes with coefficients in a group G. And again, for when I eventually do write down the map that will give us de Rham's theorem, this G will be chosen to be R. All right. There we go. Those are, we've now gotten through the two cohomology theories that we're interested in actually studying. The one bearing de Rham's name comes from composing the functor that sends C infinity algebras to this exterior algebra. Omega is what I named it. You compose him with the functor C infinity, which takes you from smooth manifolds to C infinity algebras by just taking M and sending him to C infinity MR, and by taking any smooth function and associating it to its pullback. So by composing C infinity with that omega there, we get what people usually call lambda, the typical Cartan-de Rham complex on a smooth manifold. All right, there we go. The stage is set. Now I need to start talking about the Eilenberg-Steenrod axioms, and in order to do that, I need to admit that I've kind of lied to you. The stage is not set. There's actually one more step to all of this stuff. There's something called relative homology and relative cohomology. Because it turns out that as Grothendieck and many others came to realize, what homology and cohomology are about exact sequences and about certain functors' inability to preserve the exactness of sequences. So you would really like, in whatever category on which you're defining a homology or a cohomology functor, you would really like a natural notion of exact sequence to live in that category. But unfortunately, this is not true of many of the categories that we work with, in particular, the topological spaces. Doesn't really have a nice enough notion of quotient to make an exact sequence work out. And so the solution for the category of topological spaces is to begin talking about things called topological pairs. So x, y, where x is just a topological space and y is a subspace. It turns out that that object, that pair in the category of pairs, has formal properties much more similar to a quotient object than the original topological quotient that we're used to from normal point set topology. So in a very real way, you have that something like this looks and acts a lot like an exact sequence, which means that we have a starting place for something that will eventually be called the exactness axiom. So we have something like this. So similarly, so this is for topological spaces, and in general, if we were to be talking about a spatial category, we would have to do this exact same thing. We'd have to come up with a category of admissible pairs. And in general, the morphism here might not necessarily be just an embedding. It might just be some morphism. But the typical cases we're used to, like topological spaces, it is precisely a topological embedding. In the case of smooth manifolds, you have to do the same thing as well. You don't just get arbitrary subspaces. You get closed submanifolds, and these will have to be closed embeddings in order for all of this to make sense. Similarly, we're going to need to define a category of admissible pairs for the C-infinity algebras, because there's going to need to be a relative cohomology theory for those, just as well as there's going to be one for the singular case. That ends up looking something like this. So still pairs, right? A, B. But now the relationship of these elements in these pairs is very different. Instead of this fellow, in this case, this fellow was a subobject of this fellow. In this case, because we've sort of gone through a contravariant functor, we've flipped all of our arrows around, now this fellow is a quotient of this fellow. So B is equal to a quotient by some ideal. Where I didn't bring this up already, I should have mentioned it when discussing the properties of C-infinity algebras as algebras. But it turns out that you can show, using Hadamard's lemma, that an ideal in a C-infinity algebra is just a normal, good old-fashioned ring ideal. No different. And you can quotient it, and you will still get another C-infinity algebra. So it's a category that admits nice quotients. You wind up with something like this. And now you wind up with a sequence of morphisms where, because now I have that A maps into B, A maps into B in an obvious way. And then I can go ahead and map. Actually, I did this backwards. Everything flips. So just imagine this part where I've flipped everything around and changed the order of the arrows. So I wind up with A, B, going to A, 0, going to B. And this should be not the empty set anymore, because where we were using the empty set, or the initial object in our spatial category, we will be using the zero algebra, or the terminal object in our algebraic category. And where, so I'll call this inclusion map J, or call it I, because that's an inclusion map, and I'll call this projection map P. Then where these guys actually live in these exact sequences, it's right there and right there. These maps are essentially like the identity maps. Okay, so these are the categories of admissible pairs that I'm going to be working with. It turns out there are very mild assumptions that one can make on a category of admissible pairs, such that the original category of interest can be embedded into such a category of pairs. And so the homology theory on your category of pairs will then reduce to your original absolute homology theory on your original category. The mild assumptions being that the spatial category has an initial object and the algebraic category has a terminal object. Oh God, I had those 2 clock hands completely reversed. I thought I was doing great on time. Goodness. Whoops. How does this keep happening? What, where does the time go? Okay, well, we'll try to fly through the actual Eilenberg-Steenrod axioms here. So the first 3 of these Eilenberg-Steenrod axioms won't actually require discussing admissible pairs. There are versions of these axioms that will apply on the category of admissible pairs, but once you know them for the absolute cohomology theory, homology theory on the original category, they follow immediately on the category of admissible pairs. And I mentioned it earlier, but the reason for all of these axioms, the reason we care about homology and cohomology theories satisfying all these rules, is that in a way, homology and cohomology theories are sort of like an upgraded version of a linear system of equations, right? Back a long time ago, classical mathematicians considered a problem basically done when they found out a way to convert that whatever question they had into a system of linear equations. Once you've done that, the problem is solved because we know how to deal with systems of linear equations. But as it turns out, systems of linear equations can't contain very much information. There's very hard limits on the sorts of things that they can tell you. And so homology and cohomology is just a harder algebraic problem. It's an algebraic problem that can contain more information than just the solution of a linear system of equations. And that's nice. I like containing more information in my algebraic invariance as much as the next guy. But if I can't calculate the damn thing, then it doesn't matter. That's what the Eilenberg-Steenrod axioms are for, and also Grothendieck's paradigm, which focuses specifically on the exactness axiom. The whole goal is so that at the end of the day, all that extra algebraic information that you encoded in your problem can actually still be calculated. So dimension. And sorry for all of the qualifications for this. But again, I mentioned for each one of these axioms, there are really like 4 different variations that you could come up with for both contravariant and covariant functors associating spatial categories and algebraic categories to their homology and cohomology theories, and also cohomology and homology. I'm not going to write down all 4 of them because I'm not interested in wasting your time any more than I already have. I'm just going to do it for covariant cohomology, which is also what the de Rham cohomology on smooth algebras happens to be. Okay. So we say that a sequence of functions, holy goodness. A sequence of functors, hj, each of these covariant, giving me what are ostensibly cohomology groups of some category C. Landing in the category of abelian groups could be better. It could be more general than that, but not important for us today. We say that this satisfies the dimension axiom if, and we also need C to have a terminal object. So just some category. Right now thought of as a category of like algebraic objects. So for instance, Lie algebras or the C infinity algebras that I already mentioned. So there we go. If the terminal object has no cohomology for any degree higher than 0. The analogous statement in homology would be that the homology of a point is only non-trivial at 0th order. I did last time. I mentioned how you get the cohomology from a cochain complex, but you are absolutely right. I haven't mentioned it this time. Let me do that very briefly before we actually move on, because that will certainly help clarity. Nobody cares about this anymore, right? Perfect. So I wrote this down last time, but for the benefit of everyone else here, homology and cohomology is a very general procedure that you can run on any cochain or chain complex. So like these things that I've been writing down, sequences of abelian groups with connecting homomorphisms that compose to 0. Whenever you have such a situation, you can calculate a sequence of groups from them in the following way. again, we have a cochain complex even. All co-boundary morphisms labeled for the moment to make things a little easier to see. In general, most people just call all the co-boundary morphisms the same label because it doesn't cause confusion. All right, so the fact that two subsequent co-boundary morphisms compose to 0 is equivalent to the statement that the image of this co-boundary morphism lies in the kernel of this co-boundary morphism. So image is contained in the kernel. Since, as we've defined it so far, all of these cochain and chain complexes take place in the category of abelian groups, that in particular means that we can always quotient this kernel by this image, because any subgroup is normal and hence something that we can derive quotients from. And so that is exactly what we do. We define the kth cohomology group of a cochain complex of this form. So to emphasize that, he's acting on C upper star, as I have up there. That is simply going to be the kernel of the kth map quotiented by the image of the previous map. So image of dk minus 1. Okay, what I want to say is that this association is functorial, but that means nothing if I haven't also told you what the morphisms of cochain complexes are. So I'll very briefly do that so that I can get back to what I was doing. In general, in category theory, if you're not sure what morphisms are supposed to be between objects that you constructed, just draw all the diagrams that show up and then just complete them and then ask that they commute. And then boom, you're doing category theory. So here's our first fellow. In order to have a morphism, we need 2. So here's our second. Call him B. All right, so now, like I said, just using the amazing intuition that category theory gives us, if I wanted a morphism from this thing to this thing, then I just draw arrows everywhere that it seems reasonable. And now I've got a bunch of different ways that I could go from this vertex of my graph to this vertex of my directed graph. And if every single way that I can get there coincides, we say that that diagram commutes, and that's exactly the natural condition that makes a collection of morphisms Fj into a morphism of the associated cochain complexes. So to not say it aloud, but to actually write it in symbols that we all recognize, that looks like the following. That right there. So this set of qualities for every single j is equivalent to saying that that diagram commutes, and that's precisely what it means to be a morphism. Now, this sequence of morphisms can also be associated to now a sequence of homomorphisms between the associated cohomology groups of these two sequences. So this association that I have of cochain complexes to sequences of groups is in fact functorial, which means that if I have 2 of these morphisms and I compose them together, H sends that composition to the composition of the images of those morphisms. That in particular means that if you have 2 isomorphic cochain complexes, they're sent to isomorphic cohomologies. So this is I mentioned it last time, but again, for those of us who aren't here, functors are just a very natural way to look for invariants of some category. Once you have a functor, you know that whatever it associates to any object of your original category has to be an invariant. If you had an isomorphic object in your first category, it would get sent to an isomorphic object in the target category. Okay. So yep, returning to the dimension axiom. This one alone doesn't help you calculate any cohomology besides the cohomology of the terminal object, which in the case of C infinity algebras, the terminal object is actually, excuse me, I've messed something up here. It's not clear to me immediately what it is. But the object that I need to actually be here for C infinity algebras is the real numbers, because that's the C infinity algebra associated to the one-point space. The original dimension axiom in its original context is about establishing the homology and cohomology of the one-point space. Once I've thrown that guy through the functor that associates him to his algebra, I need to have the same sort of axiom, but after I've passed through this dualizing functor. So it looks like I should have this be the initial object. All right, so C infinity alg, initial object. And now that makes a lot more sense, is just the real numbers. The set of all real numbers is a C infinity algebra. It sort of has the obvious C infinity algebra structure. Take any smooth function on n variables and just plug your n real numbers into it. Boom, you get another real number. And so what we're saying here for de Rham cohomology is that C infinity algebras have the property that the de Rham cohomology associated to R is 0 everywhere else in higher degree. But this is kind of easy. We actually saw why this is true at the very end of last talk. We know already that we have two facts. D is linear, R linear even. That follows from the chain rule property that we guaranteed that it had last time by construction. And D maps 1 to 0. We saw why that was true last time. Might as well show it again because it's really not hard to see. So it's equal to D1 times D1, or D1 times 1. But now we get to use the product rule, the Leibniz product rule. And now it's obvious. D1 has to be 0. OK, but if D1 is 0 and D is R linear, and every element of R can be calculated by just multiplying itself by 1, right? That is a representation. So we can generate all of our algebra through through multiplicative scalings of the element 1. So that means that D on R to its set of 1 forms is the 0 map. It's the 0 map. D is the 0 map, and hence every other space of forms that comes afterwards also has to be completely 0, because I'm going to somehow take the derivative of those forms to get the next one, but if all of them are 0, then there's nothing else but 0 to make the next set of forms out of. If we were interested in particular what the cohomology of R was at the 0th step, so the one that we haven't asked has to be trivial, well, it would be the kernel of this map, which is the 0 map, which is everything. So the homology, the 0th homology of R, which is just equal to the kernel of the very first map, is just all of R. So there we go. We have the dimension axiom for the de Rham cohomology on C infinity algebras. It's not all that crazy. And again, in the absence of all of the other axioms, that's all this gets you. It just gets you for the most trivial object in your space, in the case of an algebraic space, the initial object. In the case of a spatial category, a terminal object, so something like a one-point space, you can calculate that fellow. Not all that impressive, but we need that. In the presence of some of the other axioms that I'm about to write down, that becomes much more useful. Jesus. Okay, man, I told everybody that I was going to get through all of these axioms today, and that was me being pessimistic, because that meant I wouldn't get to de Rham's theorem, but I should have been more pessimistic. That's what I'm learning from all of this. Okay, well, let me at least get the homotopy axiom out of the way, because that one gives a raison d'etre for the dimension axiom. This guy is useless without the homotopy axiom. So let me go ahead and mention that. And then I will go ahead and I'll prove Cartan's the Stokes-Cartan theorem here, so you can all have seen a proof today. Okay, so the homotopy axiom. So we say that. So first, I need to give you what a homotopy looks like in my category of C infinity algebras. So we say that. Okay, actually, I'm going to write this down in general, and then I'm going to explain what happens in C infinity algebras. C to abelian groups satisfies this guy if for all, now I need morphisms A, B, C with C path connected. These are supposed to be categories of algebraic objects. So intrinsically that means nothing, but it can be given meaning in certain algebraic categories, in particular C infinity algebras, and that's what I need to happen. So if for all morphisms of this form, we have that the associated, I probably shouldn't use H for this, since I already am overloading terminology. So this fellow, composed with evaluation at some C, H, is equal to evaluation at some C prime for all J and all C, C prime in big C. I can't use big C because I already used him too. Damn it. Incidentally, none of you would like to read my notes. They're terrible. Okay. So this looks like a whole bunch of nonsense. So let me go ahead and explain what's happening here. So if I had a homotopy between two functions, that would look like something like this. H again, times the interval to y. And what I would care about are the functions that I got by partially evaluating this guy at his two endpoints, h1 and at 0 and 1. Now, if I cared about the space of functions, the space of continuous real-valued functions, sort of like the analog in the topological case for the C infinity real-valued functions on my space, if I cared about that and the induced morphism that this has on these dual objects, well, that's going to go ahead, the pullback is going to go ahead and reverse the order of these maps. And in particular, when I do this, we get CXR free product with C. Now, hopefully what I've written down there makes a bit more sense. D is something like the continuous functions on the interval, having the same connectedness that follows from being the continuous functions on the interval, where the interval is very clearly a path-connected space. So you need some analog that looks like the relationship that these guys have to this guy and this guy's path connectedness. But once you have that, what this statement looks like is that I've just taken the partial evaluation of my homotopy at one endpoint and the partial evaluation at a different endpoint, and I've said that the two images of my functor at those two different morphisms are the same. In other words, any two homotopic morphisms give the same induced morphism under homology. It turns out that this implies that any homotopy equivalence is an isomorphism at the level of homology and cohomology. And so, in the presence of the dimension axiom, if you have a space which is contractible, then you can calculate its cohomology/homology. Because you know it's homotopically equivalent to a point, you have exactly that it satisfies the dimension axiom as well. And that's how you can get off to the races. You have the simplest possible space, the initial object / terminal object of your category. You expand that up to homotopy equivalence. That gives you something slightly better. Then, in the presence of the other axioms, which I guess I'll have to write down next time, you will be able to sort of bootstrap your way up to calculating cohomology and homology of very, very complicated spaces. But for the rest of my time, I'm just going to go ahead and write down one more definition and very briefly prove the analog of the Stokes-Cartan theorem that shows up in the C-infinity setting, because it shows up in the proof of the homotopy axiom for C-infinity de Rham cohomology. And also because Dima mentioned Stokes-Cartan theorem last time, so I thought I'd make him happy. All right. C-infinity algebra. M even, a smooth manifold, and orientable. I'll mention compact. Make things simpler for myself. I'm just going to eventually have to say compactly supported with my forms anyway, but this saves me the time. Orientable, compact, M manifold. Var phi is going to be a smooth algebra morphism from my C-infinity algebra into the smooth functions on my smooth manifold. And omega is just an M form on A. Given all of this preamble, I can define the integral of omega over the homomorphism var phi to simply be the integral over M, which we're all hopefully confident exists, of, now I'll use omega M var phi acting on omega. So remember, the Cartan de Rham complex functor is a functor. It associates morphisms to morphisms of the exterior algebras that preserve filtration. And so this fellow is the mth level. He's going to send an M form on A to an M form on my smooth manifold, something that I can integrate over the entire space. So this is my definition of integration on elements of a smooth algebra, on forms on a smooth algebra. And we get very immediately from this an analog of the Stokes-Cartan theorem, which follows immediately from the Stokes-Cartan theorem. So if you believe Stokes-Cartan, then you will believe this. And this also gives some concreteness to something that I was saying with Dima at the end of the last talk. All of the algebraic properties of C-infinity algebras all essentially follow from the analytic structure of functions, smooth functions on Euclidean spaces. So once you know something for smooth functions on Euclidean spaces, or more generally smooth functions on smooth manifolds, you should expect that there's some sort of analog in the world of C-infinity algebras. Okay. All of that, except M is allowed to have boundary now. And I is going to be the inclusion of M's boundary back into itself with the induced orientation, all that nonsense. Okay, well then we have the following. The integral over this guy of, and have to drop his degree by 1. So the integral of this fellow is equal to the integral of this fellow. All right, let's go ahead and prove that. To do that, I'm not going to waste space. I'm going to use this again. So first things first, we write down our definition. This is defined as being, and remember that right now this is an m-1 form. So omega m-1. This is our whole morphism here. All right, and now I'm going to cast a spell on you where you just believe me about something. There we go, it happened. So we already know this is functorial, so we know that I can break this up over this composition. But in particular, the pullback that I associate to this inclusion is now just going to be a smooth algebra homomorphism. And if I ask about the associated mth order map on forms, the mth order pullback, it's exactly the same thing as the mth order pullback that I would have gotten using the usual Cartan de Rham complex functor, the one on smooth manifolds. So this, I also need to remember to put that there. OK. So m-1 and I circ m-1 all acting on omega still. OK. dm. Now I still have, remember, I have access to the Stokes-Cartan theorem for smooth manifolds, and this is now integration taking place on a smooth manifold. So I'm just going to run the machine along through. And I wind up with d on the outside. OK. And I also get rid of that guy when I add the d, right? Because in Stokes-Cartan, this inclusion is always there, but people usually just suppress him and don't write him. We should, though, because otherwise we're going to lose track of things if we're actually being honest with ourselves. So this one, var phi omega. But obviously now that I'm here, we know that this omega sends var phi to elements that commute with, or sends any smooth algebra homomorphism to elements that commute with the exterior differential. So I can go ahead and move the exterior differential inside. And from here, I just go back and use my definition of integration over a homomorphism to see that this is, in fact, just the integration over var phi of d omega. There we go. Very simple. All of the hard work is done at the level of smooth manifolds. If you're interested in how you actually prove it for smooth manifolds, it's a combination of working it out in the simple case of just a rectangular measure polytope, and then using what are known as smooth partitions of unity and the coordinate charts on your smooth manifold to reduce to a bunch of those cases. And this is, I think, all I have time for today. But this will end up showing up in the proof of the homotopy axiom next time. Yes?
Okay. Well, Stokes' theorem is exactly 1 to 30 quarks. So where
Stokes' theorem for smooth manifolds.
Yes, Stokes' theorem for smooth manifolds is going from here to here.
Oh, so you're using it.
Yes, I am using it. I have to. What is the shtick? The shtick is that all of the work that you did for smooth manifolds allows you to do it for all of these guys as long as the things that you're interested in integrating over are sort of like subregions of whatever space your smooth algebra lives on that look like an orientable smooth manifold. You don't get nothing. You haven't bought anything new here. It's just, and you don't necessarily need anything new in order for the homotopy axiom to run along, because you only need spaces like the interval and the C infinity algebras that live on him in order to actually pull it off. So you only get Stokes-Cartan on simple smooth algebras. So you have to send yourself to a simple smooth algebra somehow in order to get it. But you can do that for any smooth algebra and for any homomorphism that sends you there. You don't need to have like an epimorphism, which would be like the pullback of an embedding. You don't need to do that. All right, thank you. Okay, actually, I'll start from this.